All right, and welcome back. So today, let's start out with this do now, and I'm going to ask you to match the coordinate with the lines that they are on. We have line 1, y equals 2x minus 1, line 2, y equals negative 1 half x plus 5, and line 3, y equals 3x minus 4. You have three different options. We have coordinate point A, which is 3 comma 5, coordinate point B, which is negative 3 comma negative 13, and coordinate point C, which is 2 comma 4. So please match the coordinates with the line that they lie on. Remember, in order for a coordinate to lie on that line, it has to satisfy the equation. So if we substitute in the x and the y value from a coordinate point into an equation, it's going to give us a true statement. If we substitute in a coordinate point and it gives us a false statement, that means that coordinate is not on that line. So, without further ado, please try out matching these coordinates and resume when you're ready to move on. All right, so hopefully we found that for line 1, 3 comma 5 is on that line. If we substitute in 3 and 5, we get 5 is equal to 2 times 3 minus 1, and 6 minus 1 is indeed 5. Looking at the rest of our equations, could this lie on another line? Let's think about that for a second. Yeah, it can. It can also lie on line 3. If we substitute in 3 comma 5, we should get 5 is equal to 3 times 3 minus 4. 3 times 3 is 9, minus 4 is indeed 5. But does coordinate point A lie on line number 2? Let's check it real quick. No, it doesn't. Awesome. Let's talk about coordinate point B. We have negative 3 comma negative 13. If we substitute in negative 3 comma negative 13 into these equations, the only line that it will lie on is going to be for line C, or I should say line 3. I'm sorry, line 3. Now, if we go down to coordinate point C, we have 2 comma 4. Let's see what happens if we plug in 2 and 4. In that first one, do we end up with a true statement? No, we don't. What about that second equation, y equals negative 1 half of x plus 5? If we substitute that in, we indeed will be lying on that line. 4 would be equal to negative half of 2. Well, negative half of 2 is negative 1. Negative 1 plus 5 is positive 4. Will this coordinate point lie on equation 3? No, it will not. So coordinate point C will lie on equation 2. And again, this is just to jog our memory of thinking about true statements when it comes to coordinate points. For a coordinate point to be on a line, when we substitute it into the equation, we should get a true statement. And that's going to be the basis of today's topic. So please copy down today's goal. Today's goal is, in order to begin our unit on systems of equations, today I will learn how to find the point of intersection of two lines by graphing a line and testing to see if a coordinate is a solution to two separate equations. So very similarly to what we did before, where we had those coordinate points and we were seeing if they would be on the line, we're going to be taking that concept and applying it into our new topic, which is called systems of equations. We are going to be starting on chapter 5 today. So without further ado, let's begin. We're going to graph the following lines on the coordinate plane below. We have the line in red, or equation in red, pardon me, which is y equals negative 2x plus 3. We also have an equation in blue, y equals negative 2 plus 1 half x. This is still in slope-intercept form. If we were to rearrange it, it would be 1 half x minus 2. So we are still in slope-intercept form. And we know if things are in slope-intercept form, we can graph them. If we're looking at the red equation has a y-intercept of positive 3. So we would go on that y-axis and plot a point at the value of 3. We have a slope of negative 2, which means we go down 2 and right 1. Down 2 and right 1. And since we now have 2 points, we can, boom, draw a line. Look at that, fancy dancy. Let's use the same concept of graphing in slope-intercept form for our blue equation. Well, the blue equation has a y-intercept of -2. So we're going to go down on that y-axis at -2 and has a slope of 1/2, which means we go up 1 unit and right 2 units. We go up 1 and right 2. Now that we have 2 points, boom, we can draw that line. But the main question that's in that purple box, which coordinate lies, ooh, a voice crack there, whoops, that was embarrassing. Which coordinate point lies on both of those lines? Please let me know your thoughts. So which coordinate point lies on both of those lines? Well, for us to determine it, let's look and see maybe where those lines are overlapping. Because for a coordinate point to be on that red line, it would be great. And a coordinate point on the blue line, well, that's also great. But we're trying to see what coordinate point is on both lines. So if we look at what's called the point of intersection, we're going to see that we have coordinate 2, -1. So which coordinate lies on both lines? It's going to be 2, -1. And please have out your notes because we're going to jot some down real quick. We call this the point of intersection. We call that the point of intersection. It's where the lines intersect. So wherever those two lines cross over, that's going to be what's called the point of intersection. That means that coordinate point of 2, -1 is on both of those lines. And that's going to be the basis of solving what are called systems. And we're going to get to that eventually. But today, the main point is to understand the point of intersection and that it will lie on both of those lines. If we were to substitute in 2, -1 onto that red equation, it should work. And if we substitute into the blue equation, it also should work because it's visually on both of those lines. So let's talk about that real quick. Let's talk about how we're going to prove the point of intersection algebraically. So please, let me know how you think we're going to prove that 2, -1 lies on both lines. Let me know. So what we're going to do is we are going to be substituting in 2, -1 to both equations. So we have y equals -2x plus 3. The y value of 2, -1 is -1 is then equal to -2 times our x value, which is 2, plus 3. As we simplify, we get -1 is equal to -4 plus 3. And we can simplify -4 plus 3. We get -1, which means that the coordinate point 2, -1 must lie on that red equation, which is represented by the red line. But let's go on over to our blue equation. We have y equals -2 plus 1/2 x. Notice that the blue line represents every possible coordinate point that gives us a true statement for our blue equation. So if we were to substitute in 2, -1, it should be on that line. It should give us a true equation. Well, the y value is -1. Oops, let me change the color for you. Pardon me. Our x value was 2. Half of 2 is 1. So when we simplify, we get -2 plus 1, which is -1, which is also true, which means that 2, -1 also lies on our blue line, which when we plugged into the blue equation, gave us a true statement. So the main idea here is this. You should really jot this down. Since we've proven that coordinate 2 comma negative 1 lies on y equals negative 2x plus 3, that's our red equation represented by the red line, and also on y equals negative 2 plus 1/2 x, that's our blue equation that's represented by the blue line, then that must be the point where the two lines meet. Again, we call that the point of intersection. The point of intersection. So please make sure you have copied that down, because that's the main idea of what we're trying to accomplish. Prove that each coordinate point visually lies on both lines, and algebraically by substituting in the coordinate point to get a true statement. If we happen to get a false statement for either of our equations, that is not going to be the point of intersection. Let's do another example. Let's say we have the equation y equals 2x minus 5 and y equals negative 2/3 x plus 3. Well, let's first identify what our slope is and what our y-intercept is, because these are both in slope-intercept form. We're going to let the equation on the left, to help y'all out visually, be red, and the equation on the right be blue. So looking at y equals 2x minus 5, which is the red star, what is our slope? Well, our slope is the coefficient of x. It's the number attached to our x, which is positive 2. And the y-intercept is negative 5, which means we can graph this. We're going to go onto our graph. Our y-intercept is negative 5. We're going to graph on that y-axis at negative 5. Now our slope is 2, which means we go up 2 and right 1, up 2 and right 1. We have 2 points, which means we can now graph a line. To help us out, I'm just going to continue the pattern. That way, when I graph it, it's going to look a lot neater. So we now take our line and we graph. We make sure to include our arrowheads, because the line goes on and on and on. It doesn't just stop because the graph stopped. The graph could be going on into infinity, and this line goes on. Now we're going to graph that blue equation, y equals negative 2/3 x plus 3. Let's first identify our slope, which is the m value. Well, the slope is negative 2/3. It's that coefficient of x, the number attached to the x value. And our y-intercept is going to be positive 3. So when we go to graph this, we're going to graph our y-intercept, which is 3. And we're going to apply our slope, which is negative 2/3. So that means we go down 2 units and right 3. So we go down 2 and right 3. Down 2, right 3. Now again, I'm going to continue the pattern. That way it looks a bit neater for us when we graph. We're going to find our line, and we're going to graph. Again, we always make sure we include our arrowheads, because it goes on and on and on and on. When you and me party together. No, that's okay. All right. So what is going to be the point of intersection? Where is it where these 2 points line up and they hit? Where is the point of intersection? Where is that point of intersection? Well, looking at it, looks like it's going to be 3, 1. So I'm going to write our point of intersection is 3, 1. Now we have to prove algebraically that it is indeed the point of intersection. Sometimes we're going to mess up with a graph. Sometimes we might misgraph both of the equations. So we really need to make sure that we're checking algebraically to make sure we are correct. Equations is one of the things that we should never get wrong, because if we can always check our work. If it's not true, then that means we did something incorrect, which is okay, We just need to go back and fix it. So let's double check and make sure that 3, 1 is the point of intersection. Well, let's start out with our red line. Y equals 2x minus 5. We're going to substitute in our x and y value. Remember, 3 is our x and 1 is our y. So we end up with 1 is equal to 2 times our x value, which is 3. Let's simplify. 2 times 3 is 6. 6 minus 5 is 1. So we know that 3, 1 is on the red line, but we're halfway there. We're living on a prayer. We now need to check our blue equation, the blue line. Well, it's y is equal to negative 2 over 3x plus 3. We're going to substitute in our x and y value. Our y value is 1. That should be equal to negative 2/3 of our x value, which is 3, plus 3. It's a lot of threes. That's okay. We're like Steph Curry, just throwing up threes, right? So we have 1 is equal to negative 2/3 of 3 is negative 2 plus 3, and 1 is equal to 1, which is great, which means that 3, 1 is indeed the point of intersection. Awesome, awesome, awesome. I'm going to ask that you try on your own these two problems. Please try to figure out the point of intersection and prove that your answer is correct. All right, so let's go through these together. Problem number 1, we have y equals negative 5/3 x plus 3. We're going to let that first equation be red. And the second equation, y equals 1/3 x minus 3, we're going to let that be blue. We're going to graph that first equation. Our y-intercept is 3. Our slope is negative 5 over 3, which means we go down 5 units and right 3 units. So 1, 2, 3, 4, 5, 1, 2, and 3. Now that we have our 2 points, we can graph our line. This one's going to be a bit messy, but I'm going to do my best here. Make sure to draw those arrowheads. Now we're going to graph our blue equation, y equals 1/3 x minus 3. The y-intercept is negative 3. And we go up 1 and right 3. Haha. I'm going to continue the pattern because I can. And we're going to draw our line. Again, it may not be perfect, but that's okay. I think y'all are perfect. That's all that matters. So now we're going to draw those arrowheads, and let's try to identify our point of intersection. Looking at it, looks like 3, negative 2 is our point of intersection. But let's just make sure it is algebraically before we declare it. Well, our first equation, we have y is equal to negative 5 over 3x plus 3. Our y value is negative 2. That's equal to negative 5 over 3 times our x value, which is 3. Steph Curry is back because we got a lot of trees. All right, so we have negative 2 is equal to negative 5/3 times 3 is going to be negative 5 plus 3. Negative 2 is indeed equal to negative 2, which means that it will be on that red line. Now let's check our blue. We have y is equal to 1/3 x minus 3. We're going to substitute in our y value, which is negative 2. That's equal to 1/3 of our x value, which is 3. Again, a lot of threes. Steph, leave us alone. We have negative 2 is equal to 1/3 of 3, which is 1, minus 3. And negative 2 is equal to negative 2, which means that 3, negative 2 is indeed our point of intersection. Now let's go over to problem number 2. Let's let our first equation be a red line, our second equation be a blue line. We have y is equal to 4x plus 3. Our y-intercept is positive 3, and our slope is 4. So we have to go up 4 and right 1. But our graph doesn't have that. So in order for us to do that, we have to go the opposite direction for both of our axes. So instead of going up 4 and right 1, we're going to go down 4 and left 1. 2, 3, 4, and 1. If I can fit it, 1, 2, 3, 4, and 1. Haha, I can't. So now we're going to graph our line, which looks something like that. That was not perfect. So I'm going to go back and I'm going to fix it. You're going to find that when you're graphing, it may not be perfect, which is why we really need to make sure that we're checking algebraically. Second equation is y is equal to negative x minus 2. Ooh, pardon me. Which means we go down 1 and right 1, down 1, right 1, down 1, right 1. So now I'm going to graph our line. Going to do it in blue. Blue. There we go. All right. We're going to try to identify that point of intersection where our red and blue lines hit, and we get -1, -1. So let's go into both equations and check to make sure that -1, -1 is true. As you saw, my graphs may not have been perfect, so we really need to make sure that we are double checking. Well, our first equation is y is equal to 4x minus or plus 3. Whoops. So now we're going to substitute in our x and y value. -1 is equal to 4 times -1 plus 3. -1 is equal to 4 times -1, which is -4, plus 3. And -4 plus 3 is indeed -1. Now let's go over to our second equation. We had y is equal to negative x minus 2. Our y value is -1. That's equal to the opposite of our x value. Our x value is -1 minus 2. Be careful when you simplify this. The opposite of -1 is +1 minus 2. And 1 minus 2 is -1, which means that -1, -1 is indeed our point of intersection. Whew, that was a lot. Y'all are doing super duper well. Keep up the great work. I know this is a lot of arithmetic, but you're doing a great job with this. So please keep up your hard work. It's really paying off and it's fantastic to see. If you have a question, please let me know. That way we can be of best assistance for you. But you're doing really, really well. We're just going to be graphing two lines and seeing where those lines overlap. And that's, again, called the point of intersection. Keep up the great work, kiddos. If you have a question, please let me know. And I'll talk to you soon.